Here we go. All right, thank you. My name is Faye Liu, and I'll be giving this talk with my co-presenter, Chris Scott, sitting here. My co-authors include Doug Hardman, also here, Dave Cannon from Diamondback, and my colleagues at RevoChem, Muqing and Jiang. All right, with that, I will actually today talk about an interesting topic on the difference between drainage rock volume and the well-accepted stimulate rock volume. And I'll give the key concept of what's the difference, by definition, what's what we mean by stimulate rock volume and what's the drainage rock volume, and talk about geochemical fingerprinting technology, which is helping us to understand the drainage rock volume in general. And then I'll give it over to the expected case study from Chris from Diamondback directly. All right, so with that, I would like to first step back a little bit and think about the process that hydrocarbons are being produced from those unconventional reservoirs. So here is a cartoon, right? First, we're given the geology. We're given the rock, right? The geology where we have porosity in it, permeability in it, saturation in it. All those things are given. There's nothing we can do about it. We can characterize them. It's static, and we have been studying it for at least the mud rock, 20 plus years. So we have good amount of knowledge about it. The next thing is we give those rock to our wonderful drilling and completion engineers. They drill a well and they frack it, right? And there's another layer of complication going in there, which is different completion styles, stages, how much propane you put in there, how much fluid you put in there, to generate this, what is called stimulated rock volume. By definition, the stimulated rock volume is a one-time thing. You stimulate it and call it stimulated rock volume. That stays the same. So it's a one-time thing. It's not going to change. However, are you going to drain the entire stimulated rock volume that you stimulated? You could frack, you could pick up on this microseismic or fibers, some might hurt over 1,000 feet. But do you believe you're effectively draining all that 1,000 feet or 500 feet, right? A very important concept we introduce here is what's called drainage rock volume, where those hydrocarbons are drained. So you have to have all those favorable geology conditions. You have to have it stimulated. However, you have to have some other things for it to be able to drain from it, right? There are also other operational events that are impacting those. There's frac hits, there's pressure communication. All those put on ESP, all those would impact your drainage. And this drainage is not static. It varies significantly from the over 2,000 well we've been monitoring, that it could change significantly through time. So there's another layer of complication going into the drainage. That's what we are going to talk about. And the drainage is about what you make money from, right? About those oils that end up in your separator, in your stock tank, and become your revenue. So that is actually the least studied. That concept has been introduced about 2017, and so we have less year, about 5 years knowledge of studying those drainage rock volume. So the most direct way to study drainage is by studying what gets drained, which is the oil. There are actually thousands of compounds that are naturally occurring compounds in the oil that serve almost like a natural tracer to tell us about those fluid flow. So what you're looking at here, get my laser pointer here, is from one of the multi-dimensional gas chromatography with the advance of chemical analysis tool. Now we're able to resolve much more compound. This is from what we call GC by GC. Every compound here, every peak that you see here represent a different compound. And you can zoom in to a given area, and there are more compounds in there. So there's routinely over 2,000 compounds in every drop of oil, whether it's directly from a produced oil or oil extracted from rock. And those compounds carry tremendous amount of information. Why? Because the geological processes actually left behind a lot of traces in those oils, in the rock, and also in those oils that are in the rock. It varies vertically for various reasons. The obvious reason is different organic origin, right? Different organic origin, your avalon, your WolfCam. But it's not just that. It's also different depositional environment, different mineralogy, and migration, right? Even if it's sourced the same, let's say your hydrocarbon, when it's migrated from your WolfCam A to your serbon sand, it's passing through rocks that have kerogen, it has bitumen, has clay, and many other things in it. Then certain compounds have higher affinity for certain mineralogies, so that those compounds tend to accumulate in those source rock, while others move faster and accumulate in those reservoir rock. So those are also causing those fine granularity differences every 10, 15 feet of rock to current extent of our analytical tool, be able to confidently capture that difference. But that difference is really in the fine granularity. So really thank you to the advancement of those chemical analysis tools. Traditionally, we're only able to resolve less than 100 compounds in a drop of oil. That's good enough to tell the difference between avalon to the WolfCam A. However, not enough to tell the difference within the WolfCam A, the upper, mid, lower. So now with over 2,000 compounds, we're able to see that. So with that, there are actually two kinds of geochemical fingerprint information. One is from oil extracted from the rock. The other is directly from produced oil. So using oil extracted from the rock, we built a product called reservoir characterization indices. So it's similar to it's compared a lot to other petrophysics tools that's able to tell us, indicate oil saturation, oil in-place index. What's behind this is easy. You actually load the same amount of rock every time and look at total oil extracted. And the second thing is the reservoir quality index, which is a matrix permeability index indicator. So essentially, think about it. If everything else equal, when you pull those rocks from the subsurface, let's say cuttings, from the subsurface to the surface to the lab, there's inevitably some loss. The more permeable the rock is, the more loss you have. So we built an algorithm using that to indicate the matrix permeability. The next step is that we collect the produced oil, collect also the geochemical fingerprint information from the oil, and compare it back to the cuttings to see where the oil produced from, so that you can actually generate a profile to see what's the percentage quantitatively coming from each of the 10, 15 feet. So that is what Chris will be focused on, so I will not talk too much on that. I'll leave it to Chris to talk. But I wanted to quickly talk about what the fundamental of how we can calculate percentage coming from each of layer of rock. So the geochemical-based production allocation is nothing new. It's coming from the 80s and 90s from a group of geochemists from Chevron. It was originally used for oil leakage. You have in the middle of the ocean some oil leak, trace it back to where it's coming from, and then it's used in lawsuits. So it become published, and now it's commonly used for conventional reservoir for royalty calculation. Its application in the unconventional reservoir is relatively new because traditionally the resolution is not enough to tell the fine granularity difference within the unconventional reservoir every 10, 15 feet, the resolution we need. However, now we have the tool. So fundamentally, it's actually very simple. I want you to draw your eyes to three of the compounds here, which is interested in those are chemical structure. So when we say geochemical fingerprint, it is the relative abundance between different compounds, because no matter where the oil is from, North Sea, Eagle Ford, Permian, it's going to include a similar 2,000 compound. The difference are in the relative abundance. So you see those biphenyl versus 2-methylnaphthalene ratio. It's 1 in the base of the serbon sand. This is actually a Permian case. It is getting smaller as it gets deeper. This is upper WolfCam A, and this is getting lower part of the WolfCam A. We collect the produced oil, it's 0.385. Essentially, we're just building a linear regression model to mix a 1.85, 0.52. My eyes is not, didn't wear my glasses. I hope the number is correct. But anyway, to make a 0.385. As simple as that. It's a linear regression model, very simple. The only difference is that you have thousands of compounds. So you actually have thousands of equations so that you can come up with a unique solution, right? So that's why we need the high resolution. If you look at those three compounds, it's actually between your normal alkane 13 to 14. If you use your regular GC, if you're using your old traditional method, it's going to bury it between those very tiny peaks. So the difference are there. The distinction are there. It's just previously we did not have the right tool to capture that fine granularity difference. Now we have it. So that's the model itself is very simple. There's nothing fancy about it. It's only because we have more information. Okay, so this is my last slide, just a general workflow. So the workflow goes that you collect your cuttings vertically. So the horizontal is not for phase one, it's more for advanced, because geology change much faster vertically than it change laterally. You profile it, generating the indices to see where you have the highest saturation, where you have the highest permeability, and then you collect your produced oil. You're profiling both and using those geochemical information. Essentially, you're digitizing your oil and then using that to build your model to calculate the percentage, right? So that's the fundamental of it. With that, I'll hand it over to Chris.
Left. Get that guy on there. Yeah, I'm just gonna have to hold it. All right, thank you, Faye. Now let's go over some case studies as performed by Diamondback. So a couple years ago, Diamondback had begun a cube-type development in the subject field. And so some data collection projects were put in place to help analyze the strategy, the initial strategy in this cube development. So some of the initial questions that we had for RevoChem were, what are our overall drainage heights for each target interval? What, do we have drainage overlap by having targets too close together and therefore competing for similar reservoir? Conversely, have we bypassed some reservoir by putting some targets too far apart? What's the temporal production variation in terms of gross height and the facies within the productive intervals? And to that point, what facies are the significant contributors? So we collect have our cuttings analyzed, we collect our oil samples from our horizontals, RevoChem releases the data to us, and we integrate that into our petrophysical model. And we've compared that to a microseismic project. And we'll go ahead up front and talk about some of the conclusions and some of the observations. We've been able to identify the recoverable hydrocarbons in the facies that they reside in. And that way we've been able to optimize our landing zones. We've been able to target those facies and balance that with having enough vertical separation so that we don't have that competition over reservoir. In turn, that leads us to identifying the targets that we can that can remain stacked and those that require staggering development. Finally, the geochemically derived results from RevoChem and the indices that we get with oil in place and the reservoir quality index, as Faye mentioned, we're able to validate that or cross-check that with our log-derived petrophysical indices. And in the future, the goal is to integrate that into frac and reservoir modeling. So the case studies occurred here in northwest Martin County in the northern portion of the Midland Basin. We collected samples at 20-foot intervals in the formations represented on the type log to the right. And in the middle here is a gun barrel diagram. And note the development order here. The westerly pad was first. 7 months later, we came in and put the second pad online. And then the pad in the middle was 8 months after that. And that's where the microseismic study occurred with the wells that were monitored highlighted in green. So now we'll talk about the stimulated rock volume as defined by the microseismic project versus the RevoChem-derived drained rock volume. Now it's important to note here, while we're comparing microseismic results, we are solely looking at height here and not frac half-lengths. So your eyes are probably drawn immediately to the image down here at the bottom. So the purple and red cloud, if you will, is a DPA-derived cluster density cloud for all the frac stages for wells 7A, 7C, and 7E in a gun barrel view. And we also monitored wells 6B, C, and E, but this display is just showing the cloud for the 7 series wells. And those illustrate the areas where the highest degree of deformation occurred. I don't have time to go into DPA, but that's the dynamic parameter analysis performed by the vendor, microseismic vendor, and it's just a more robust or more stringent analysis way to display these events as opposed to all the events in a cloud. So the bar graph on the top there is plotting the average P90 RevoChem heights for all the wells in the field in dark blue, and plotted against that in light blue are the average DPA microseismic heights. We see in formation A, we have a greater height in the DPA microseismic, and then in formation B, we have a greater heights in the dark blue in the RevoChem. And this is kind of interesting because the targets are actually very close stratigraphically. Now, I should have mentioned here, we do have this petrophysical plot that the microseismic plot is laying on top of, where we have some raw logs on the left, some petrophysical interpretations, formations kind of identified by the color code is used throughout the formation, or throughout the presentation, excuse me. The arrows indicate where in the formation we targeted each formation. Moving on to, this stratigraphically close A and B targets, and seeing that discrepancy, that could be due to stratigraphic complexity. We have quite a bit of heterogeneity within the A and B formations. There's also a structural component here. We have pretty high quality 3D seismic survey across this area, and we've noticed the curvature features, which previous presenter did a very good job of explaining. And with those curvature features, we might have more natural vertical fractures. So that could be playing a part into the discrepancy. Moving down into formation C, we see much more agreement between the two data sets. It's hard to get much closer than that, really. And I'd say a pretty reasonable alignment as well in formation E. So to kind of qualitatively sum up the common findings between RevoChem and microseismic, we have these bullet points here that kind of correspond with the image below. First, the vertical drainage profiles of targets A and B from microseismic and RevoChem indicate significant overlap. They also indicate good near wellbore stimulation and drainage with limited downward growth, which brings us to point 2. We have some bypassed reservoir there in formation B. So in a nearby block, we actually lowered our target in the B. We were able to access that previously untapped reservoir. Point 3, we observe in both data sets that one landing zone is sufficient to drain the entire C formation. However, point 4 outlines how both data sets indicate overlapping stimulated rock volume and drainage rock volume. So where formation E is prospective, we definitely need to move that formation C target up if the petrophysics supports that. So here's a cleaner version of and cleaner display of just the RevoChem, no microseismic there. And this is for all wells that we've done across the field, not just the microseismic area. So you probably notice here that we have very consistent results, very consistent drainage profiles, even getting 3 to 4 miles away from the initial project. And the arrows again are, excuse me here. The arrows here are indicating where the landing zones were for each formation. And note here, yeah, we moved that B target down. So two important things here we learned from RevoChem. We are now accessing the previously bypassed reservoir, and now we know we definitely need to stagger these in our development. We see that we do not have any significant overlap between formations B and C. Check, that's good. Between C and E, again, we see some overlap, Doesn't look as extreme as this, but we have found that this can be detrimental to production and well quality. So again, we know that we need to stagger these landing zones, or maybe even talk about moving that landing zone up. And the red call-out boxes, they're kind of a teaser for the next slide. Notice that the landing target is getting very little contribution. So this is an example of formation E wells across 7 different blocks across the field. And notice the drilling target here, it was a high TOC, high gamma ray interval that was picked for drilling efficiencies and geosteering purposes, but we get very little contribution out of it. Highest contribution, in fact, is coming out of this siltier facies above the landing zone. Now you might say, well, come on, Chris, that's pretty close. You're going to frack into it anyway, right? Well, we have data, hard evidence, to show that moving even that little bit into the more preferred facies will equal better production. And stratigraphy certainly matters. It's being a siltier facies, it's not everywhere, and as porosity changes, complex deposition. So your due diligence and geologic mapping is certainly paramount. Now let's talk about the temporal production variation. And with the major trends, we see once again that we have very consistent vertical drainage profiles, despite the fact, in this example, we began analysis at various points in these wells' life cycles, which are highlighted by the red boxes. This well we began the analysis 4 years into its life, and then 2 years into those wells' lives, immediately after frac, and so on as you move right. Very consistent, right? I'd like to see that. And then the bottom image here is provided by RevoChem. This is a single well and analyses, so we took samples at these timestamps, and so the image here is showing you the percentage of contribution from each formation at each timestamp. However, we do see fluctuations within discrete strata temporally. So this image, also provided by RevoChem, is again one well, a formation E well, and we have 13 different timestamps that we took these samples. And in the bottom, as Faye kind of explained, we have these we've quantified, or they have quantified, the contribution from each 20-foot interval. Remember, that was the sample interval in our vertical baseline well, the cuttings collection. And notice, again, where we put the well, not much contribution, and then right above that in the siltier interval, much more. And I will actually click through all 13 of these timestamps, and you'll see the production kind of ebb and flow from each one of these intervals. And so we started on kind of a weekly sample rate, maybe missed a couple there, went to more of a bi-weekly sample rate. Okay, here we go. And watch as things kind of change. And we kind of forgot about it for 3 months or so, or avoid analysis there, and then came back for a couple weeks in 32 and 33. So what causes these fluctuations? Is it just natural variation? Is it offset operations in the form of ESPs going down, pump jack activities on your verticals, nearby frac operations? Probably all of the above, right? We've actually observed some of that ebb and flow from some of the operations. Luckily, a lot of these major trends remain stable. There we go. So in conclusion, Diamondback certainly has learned a lot from the RevoChem analyses, but it was that integration of microseismic and the DPA analysis that gave us confidence that, you know, we have 2 independent data sets that were collected in extremely different manners and aligning to the same outcome, right? So that allows us to believe we can use this across the field. Microseismic absolutely certainly still has its place in that we have not, talked about XF at all. And so your lateral spacing laterally is an important factor. And again, these outcomes, recoverable hydrocarbons and what facies they exist in, those have been identified. That allowed us to optimize our landing zones by adjusting our targets into those best rock possible while balancing a sufficient vertical separation. We've identified what can remain stacked, what needs to be stackered. The geochemical validation into our petrophysical model was very encouraging. They aligned quite nicely, but not everywhere. and so that means further analysis should be done. So as a lot of people in the room probably know, the more variables you can constrain in any kind of modeling aspect is certainly, it's going to make those models much more accurate. So if we can constrain height, we feel good. So that's kind of the future value that we see with these data sets is the frac modeling and reservoir modeling. So Faye and I would like to acknowledge and thank Hannah Chittenden for her guidance on the microseismic work, our Diamondback management for approval to show you this today, and certainly Diamondback field team sample collection. That's a little bit more daunting task than some people are aware of. So, thank you.